Good morning, students. Welcome to 11th standard physics class. Students, today's topic is on waves, unit 11. In the previous chapter, we have discussed the acceleration of particle. Consider a medium which consists of collection of particles. If the disturbance is created at one end, it propagates and reaches the other end. That is, the disturbance produced at the first mass point is transmitted to the next neighboring mass point. Thus, the disturbance which carries energy and momentum from one point in space to another point in space without the transfer of the medium is known as wave. Next, ripples and wave formation on the water surface. Suppose we drop a stone in trough of still water. We can see a disturbance produced at the place where the stone strikes the water surface. We find that the disturbance spread out in the form of concentric circles of ever increasing radii and strike the boundary of the throw. This is because some of the kinetic energy of the stone is transmitted to the water molecules on the surface. On the water surface, the stiff moves up and down when the disturbance passes on the water surface. This shows that the water molecules only undergo vibratory motion about their mean position. Formation of waves. Let us take a long string and tie one end of the string to the wall. If we give a quick jerk, a bump is produced in the string. Such a disturbance is sudden and it lasts for a short duration. Hence, it's known as a wave pulse. Its jerks are given continuously, then the waves produced are standing waves. Similar waves are produced by a plucked string in guitar. Characteristics of wave motion. For the propagation of the waves, the medium must possess both inertia and elasticity, which decide the velocity of the wave in that medium. In a given medium, the velocity of a wave is a constant whereas the constituent particles in that medium move with different velocities and different positions. Velocity is maximum at their mean position and zero at extreme positions. Waves undergo reflection, refraction, interference, diffraction and polarization. That's all. Next, mechanical wave motion and its types. Wave motion can be classified into two types: mechanical waves and electromagnetic waves or non-mechanical waves. Mechanical waves which require a medium for propagation are known as mechanical waves. Example, sound waves, ripples formed on the surface of water. Non-mechanical waves. Waves which do not require any medium for propagation are known as non-mechanical waves. Example, light. Further, we can be classified into two types of transverse waves, longitudinal waves. Transverse waves means short waves. Longitudinal waves means long waves. Next, transverse waves. In transverse wave motion, the constituents of the medium oscillate or vibrate about their mean position in a direction perpendicular to the direction of propagation of waves. Next, longitudinal wave motion. In longitudinal wave motion, the constituent of the medium oscillate or vibrate about their mean position in a direction parallel to the direction of propagation. The next, terms and definitions used in wave motion. Suppose we have two waves as shown in figure. The two waves are both sinusoidal. There are many differences between them. Therefore, we have to define some basic terminologies to distinguish one wave from another wave. Consider a wave produced by a stretched string. Here, the mean position is horizontal line zone. The highest point in the shaded portion is called crest. with respect to the reference level. The lowest point on the unshaded portion is called trough. The wave contains a repetition of section O to B. And hence we define the length of the smallest section without repetition as one wavelength. The length OB or length BD is one wavelength. A Greek letter lambda. Lambda is used to denote one wavelength. The next, wave of different amplitude. The waves have same wavelength, same frequency and same time period and also move with same velocity. The only difference between two waves is the height of the either crest or trough. This means the length of either crest or trough. The height of the crest or trough also signifies a wave character. So, we define a quantity called the amplitude of the wave. The next topic, velocity of transverse waves in a stretched string. Let us compute the velocity of transverse traveling waves on a string. When a jerk is given at one end of the rope, the wave pulses move towards right end with a velocity v. This means that the pulse move with a velocity v with respect to an observer who is at rest frame. Suppose an observer also moves with the same velocity v in the direction of motion of the wave pulse. Then that observer will notice that the wave pulse is stationary and the rope is moving with pulse with the same velocity v. Okay. Consider an elemental segment in the string. Let A and B be 2 points on the string at an instant of time. Let dl and dm be the length and mass of the elemental string. By definition, linear mass density mu is equal to dm by dl. The mass by length. So, dm is equal to mu dl. The element string AB has a curvature which looks like an arc of a circle with center at O, radius r, and the arc substituting an angle theta. The observations. The velocity of the string is directly proportional to the square root of the tension force. The next, inversely proportional to the square root of the linear mass density. Next, independent of shape of the waves. That's all. The next topic is velocity of longitudinal waves in an elastic medium. Consider an elastic medium having a fixed mass contained in a long tube whose cross-sectional area is A and maintained under a pressure P. One can generate longitudinal waves in the fluid either by displacing the fluid using a piston or by keeping a vibrating tuning fork at one end of the tube. Let us assume that the direction of propagation of waves coincides with the axis of the cylinder. Let rho be the density of the fluid. The initially at rest. At t is equal to 0, the piston at left end of the tube is set in motion towards the right with a speed u. In time interval del t, the distance moved by the piston del d is equal to mu del t. Now, the distance moved by the elastic disturbances is del x is equal to v del t. Let del m be the mass of the air, velocity v, time del t. So, del m is equal to rho a, del x is equal to rho a, v del t. Okay students, today's topic is over. Today's homework. Students, I have given homework from this topic. Read the questions and answers well and then write in your fair note. Thank you students. God bless you.